All right, today we're basically becoming scientific detectives. We're on a mission to figure out how scientists measure something you can't even see, the energy that's released as heat. So think about it. This is our central mystery. You mix two chemicals together and poof, it gets hot. But how much hot? It's not like you can put the heat on a scale or measure it with a ruler, right? Well, it turns out there's a really clever way to trap it and figure it out indirectly. Okay, let's kick off our investigation. To really crack this case, we first have to get a handle on the basic principle behind how you can possibly trap and measure something like heat. This whole field has a name, of course, calorimetry. And at its heart, it's really just the science of carefully tracking where energy moves when something happens, whether that's a chemical reaction or just something cooling down. The way scientists tackle this is pretty smart. They basically split the universe into two parts for the experiment. First, you've got the system. That's our source, the thing making all the heat. And then you have the surroundings. That's everything else, specifically our specially designed heat trap. And the whole reason this works comes down to a super fundamental rule of physics. Energy can't just be created or destroyed, it just moves around. So any heat that our system loses, our heat trap has to gain. It's a perfect one-to-one transfer. And this slide really nails the core idea. The amount of energy is conserved. So if we can measure exactly how much the surroundings heated up, we know precisely how much heat the system kicked out. It's a simple idea, but it's incredibly powerful. So if we're going to measure heat, we obviously need a tool for the job. We need to build our very own heat trap, which in the science world is called a calorimeter. Now, you might be picturing some crazy high-tech piece of lab equipment, but a basic calorimeter can be ridiculously simple. I'm talking two styrofoam cups, one nestled inside the other, some water to soak up the heat, and a thermometer to see how much the temperature changes. That's it. That's our heat trap. Now, in a perfect world, in a perfect experiment, every single last bit of heat released by our reaction would go straight into that water. And if that happened, measuring the water's temperature change would tell us the whole story. But here's the catch. Is our little styrofoam setup really perfect? What about the cups themselves, or the thermometer, or even the air trapped inside? Don't they absorb a tiny bit of heat too? And the answer is, yeah, of course they do. So what's really happening is that the heat actually splits. The vast majority goes right into the water, just like we want, but a little bit gets kind of siphoned off by the calorimeter itself. The cups, the thermometer, the whole shebang. Think of it like a tiny heat tax we have to account for. And that means our simple equation needs a little upgrade. The total heat that came from the source is actually the heat the water gained plus the heat the calorimeter gained. If we just ignore that second part, our final answer is going to be wrong. So, how in the world do we figure out that heat tax? It's not like the cup is going to tell us how much energy is soaked up. No, we have to be clever. We need to calibrate our instrument. The way we do this is by using a chemical reaction where we already know exactly how much heat it's supposed to produce. We'll use a classic, the neutralization reaction between hydrochloric acid and sodium hydroxide. It's our reliable benchmark. Yep, scientists have done this reaction countless times, and they know that for every mole of water you create this way, exactly 57.9 kilojoules of heat are released. That number is our anchor. It's our ground truth. So here's the game plan. We run the reaction inside our calorimeter. We see how hot the water gets. We use that to calculate how much heat the water soaked up. And since we know the total heat the reaction should have made, any heat that's missing, well, that's the heat tax. That's the amount that went into the calorimeter itself. And just like that, we found it. Okay, our tool is now calibrated. We know its unique personal heat tax. Now we can use it to investigate an unknown, to find a hidden property of a really common material, aluminum. The procedure here is pretty straightforward. We heat a piece of aluminum to a very precise temperature, let's say the temperature of boiling water, 100 degrees Celsius. Then we quickly drop it into our calibrated calorimeter and measure the final temperature once everything settles down. Now we just work backwards. We can calculate the heat the water gained. We can also calculate the heat our calorimeter gained using that special heat tax value we just found. You add those two numbers together, and that grand total must be equal to the amount of heat the hot aluminum lost. We've measured the unknown. And when we run the final calculation, we can determine a fundamental property of aluminum called its specific heat capacity. And what's amazing, as you can see on this chart, is that the value we get from our simple styrofoam cup experiment is incredibly close to the officially accepted scientific value. I mean, not bad for a couple of coffee cups, right? So our detective work totally paid off. We found a number for aluminum. But why does this number, this specific heat, actually matter in the real world? Well, specific heat capacity is basically a material's thermal fingerprint. It tells you how much energy you have to pump into something to heat it up or how much it has to release to cool down. It's really a measure of how well a substance can store heat.
And this property is absolutely everywhere. A low specific heat is great for a frying pan because it means it heats up really fast with very little energy. But water has a super high specific heat, which is why it's the perfect coolant for your car's engine. It can soak up massive amounts of heat without getting too hot itself. And that exact same property is what allows our planet's oceans to stabilize the entire global climate.
And this all brings us to a final, really interesting thought. We've seen how a pretty simple experiment can reveal a fundamental property of matter. But what if we could design materials with the perfect specific heat for any job we wanted? Imagine a phone that never overheats, or buildings that could stay cool without any air conditioning. By understanding this invisible world of heat, we can start to engineer a much more efficient future.